Hello everyone, my name is Trevor Zhang. I come from T3Go. I'm currently responsible for building T3Go's data lake ecosystem. It's my honor to participate in the Data Orchestration Summit and share how we build a high-performance data lake with Apache Hudi and Alluxio at T3Go. This is an ongoing project by me and my colleague Vino Yang. Today, I hope to discuss with you some of the pain points our team faces in the construction of the data lake and our practice to solve these pain points. Today's talk will follow this agenda. A brief introduction of T3Go's data lake, why we built it, and the problems we have encountered. Then we will cover Apache Hudi's adoption, and finally we will go over some practical experience and lessons learned in building our data lake around Hudi and Alluxio at T3Go. Before we dive in the data lake, I would like to first introduce T3Go's background. It will help us to understand why building a data lake is critical at our company. T3Go is China's first platform for smart travel based on the Internet of Vehicles. As a company is driven by the Internet of Vehicles, we have aggregated massive amounts of data from each end of people, vehicles, roads, and clouds. The data at each end has its own application scenarios, and these scenarios are not isolated, but require collaborative analysis to work together. To enable T3Go smart travel, there's none other suitable solutions than a data lake to carry such diversified data and make the best use of that data. Okay, so that's the background that we have at T3Go. Now let's move on to the main topic. Since we are talking about the data lake, let's first understand what is a data lake. A data lake is a centralized repository that allows users to store any type of data and use it for various scenarios. For a long time, data warehouses have been using shared nothing architecture. This architecture has many advantages. Tables are horizontally partitioned across nodes. Every node has its own local storage. Each node is only responsible for its local table partitions. It's got an elegant and concise processing mechanism memory. Scales well for star schema queries. It's also a typical architecture for data warehouse. However, today as computing and storage requirements are getting higher and higher, its disadvantages are becoming more and more prominent. It couples computer and storage resources, limited elasticity, limited availability. Inspired by the Snowflake paper, we implemented the multi-cloud shared data architecture. Let's take a look at the characteristics of this architecture. There's no data silos. It is native for struct and semi-struct data. Data can be scaled along many dimensions, and it allows bulk loading, reporting, exploration, and analysis. This multi-cluster shared data architecture brings obvious improvements to T3Go's data lake. It guarantees all data in one place, independently scale storage and compute. No unload, reload to shut off compute. Every virtual warehouse can access all data. This picture shows the overall data lake architecture at T3Go based on the multi-cluster shared data architecture. There are 5 layers from top to bottom. The bottom layer is a storage layer mainly based on HDFS and OSS. We plan to be more based on OSS in the future. At present, this public cloud and private cloud coexist at the same time. Above it is a storage interface abstraction layer. And then we added the Alluxio, an open source unfiled data orchestration layer, as our memory acceleration layer that separates storage and computing. On top is the data organization layer. At this layer, we choose Hudi as a data lake framework. Going up is a specific application layer. On the side, we also provide metadata storage and data lake governance related capabilities. What is the obvious difference between a travel business and other businesses? A typical attribute of travel business is the problem of long tail payment. This means that the act and the goal of traveling may be achieved within a limited time, but the act of payment is uncertain. Though most of users choose to pay shortly after the trip is completed, there are still some users who choose to pay right before the next trip. This is very different from scenarios where conventional big data manually analyzes multiple types of data. This feature alone brings us great challenges, such as long business window leads to high cost of business analysis, backtracking. Orders are generated when trips are booked. Due to the long tail of the payment, a long business window is formed, which directly leads to a relatively high retrospective cost of order analysis. Simply put, the components of an order are driver, passenger, car, and trip. When designing, there's usually an order master data table, which is then associated with dimension tables corresponding to other elements. The order table usually only generates one piece of data for an order, and then the date is updated when the order status changes. We assume that an order was initiated half a year ago, and the order was completed half a year later, but our analysis manually revolves around the date half a year ago. For example, half a year has passed and the driver's mobile phone or passenger's personal information has changed. How do we quickly go back to the historical version of each table half a year ago? In the Hadoop data warehouse, it is difficult for us to do this quickly. We can only record all changes as immutable events, but correlation analysis based on such events is very troublesome. The above pain are mainly caused by the ununiqueness of the travel business. Next, let's look at a data ingestion pipeline related problem. For example, the data ingestion pipeline cannot guarantee reliability. The conventional model of the big data warehouse is to synchronize the data from the business system to the warehouse through ingestion methods, and then the big data analysis development business logic on it and output reports for display. But we often encounter many unstable problems in the data synchronization pipeline. These three figures are very common problems such as partial write success, dirty data caused by business logic errors, and repeated retransmissions caused by network jitter. By the data ingestion pipeline is unstable. It also causes the unreliability of data in the warehouse, which indirectly leads to the inaccuracy of report data. To sum up, we found that the Hadoop data warehouse system has some typical pain points. For example, its SLA is very low. The latency of the data pipeline is very high. There are small file problems. It doesn't support data version management and it doesn't support incremental processing. These are the reasons we can't use it for our data lake infrastructure. Okay, we just now introduced why to build a data lake instead of just using the Hadoop data warehouse. Let's move on to our second topic. We will briefly introduce the data lake framework of Apache Hudi and explain how we solve these pain points of Hadoop through the Hudi framework. Hudi is the acronym for Hadoop abstracts, deletes, and incrementals. We can see from the name that the problem it wants to solve is very intuitive. Hudi currently manages the distributed file system at the ultra-large scale analysis dataset on the cloud at Uber. According to public data, it has exceeded 150 PB. It joined the Apache incubator in January 2019 and graduated and was promoted to TLP in May 2020. Hudi has many features that have doesn't support. We will not introduce all of its features here, but there are several that solve the pain points we listed in the first topic. There's ACID semantics of transaction writing, support incremental processing, storage management, and time travel. We will take another look at these related features later. Next, let's take a look at Hudi's architecture. Hudi itself has a plug-in and very simple and clear architecture. Its core ranger is part framed by the dotted line in the figure. Among them, only the dark blue timeline method is fixed, and the other, including indexes and the data formats, are expandable. Of course, because many storage systems maintain compatibility with the HDFS interface, the storage system is naturally a replacement. In addition, we see that there's a very rich ecology on the right side and the read side. Next, we introduce the storage modes and the core views supported by Hudi. Hudi supports different storage modes for read-heavy and write-heavy, and different storage modes support different core views. In addition, different core engines have slightly different support for core views. Here we show a support metric. Okay, after introducing some of Hudi's features, let's take a look at how it solves the problems we encountered in the Hadoop data warehouse. The first is an extremely long business window caused by the long tail of the payment, which leads to the problem of high retrospective costs for order-based analysis. Let's see how Hudi's time travel query can turn back time. Still in the previous scenario, when an order is completed, we will go back to when it was created using the timeline capabilities provided by Hudi, so that all relevant table snapshots are loaded back to the version the 1st of June 2020. So it's much easier to conduct related analysis on the order. Finally, let's address the issue of how to ensure the reliability of the data intake link. We have given answers to the three difficult questions mentioned earlier. First of all, the problem of a partial failure is based on the atomic nature of Hudi transaction writing. In this case, data will not be released to the data warehouse, which means that incomplete data writing is invisible. Dirty data is found. It doesn't matter. The entire commit can be rolled back. The data duplication problem of failed retransmission is caused by the unstable work, which can also achieve idempotent updates by using the absurd feature of Hudi. Now, we will talk about the practice of building a data lake based on Hudi and Alluxio at T3Go. In the early version of our data lake without Alluxio, data received from Kafka in real time is processed by Spark and then written into OSS using Hudi data streamer tasks. With this architecture, Spark often suffered high network latency when writing to OSS directory. Since all data is in OSS storage, OLAP queries on Hudi data may also be slow due to lack of data locality. To address the latency issue, we deployed Alluxio as a data orchestration layer, co-located with computing engines such as Spark and Presto, and use the Alluxio to accelerate read and write on the data lake. We mount the corresponding OSS path to the Alluxio file system and set Hudi's target base path parameter value to use the Alluxio schema in place of OSS schema. Spark pipelines with Hudi continuously ingest the data to Alluxio. After data is written to Alluxio, it is asynchronously persisted from the Alluxio cache to the remote OSS every time. These modifications allow Spark to write to a local Alluxio node instead of writing to remote OSS, significantly reducing the time for the data to be available in data lake after ingestion. Let's look at two cases where Alluxio and Hudi are used in combination. First case, this picture shows the pipeline of data processing. The provider's streaming data comes from Kafka and then it is connected to Flink for streaming consumption. Flink writes the data into the Hudi data lake in a low latency form. And after the data is written and submit, the app engine, Zipline, and DaVinci call service such as Presto and Clean to load the Hive table in Hudi format from Alluxio. For example, we use Presto as an 80-hook query engine to analyze the Hudi tables in the lake, co-locating Alluxio workers on each Presto worker node. When Presto and Alluxio service are co-located and running, Alluxio catches the input data locally in the Presto worker, which greatly benefits Presto for subsequent retrievals. On a cache hit, Presto can read from the local Alluxio worker storage at memory speed without any additional data transfer over the network. In the second case, Spark loads the Hudi date from Alluxio, and the processed date is still written to Alluxio. In the data warehouse processing, many intermediate data from are thermal data benefit from Alluxio's good support for thermal data. The data processing pipeline time is greatly shortened. It also ensures the stability of the processing data cluster. After comparison and verification, we choose to use Spark SQL as a query engine. Our performance testing queries the Hudi table, comparing Alluxio and OSS tickets against the OSS directory as well as HDFS. In the stress test showing above, after the data volume is greater than a certain magnitude, the query speed using Alluxio and OSS surpasses the HDFS query speed of the hybrid deployment. After the data volume is greater than 100 million, the query speed starts to double. After reaching 600 million data, it is up to 12 times higher than query native OSS and 8 times higher than query native HDFS. The improvements depends on the machine configuration. Based on our performance benchmarking, we found that the performance can be improved by over 10 times with the help of Alluxio. Furthermore, the larger the data scale, the more prominent the performance improvement. So those are our learnings from building T3Go's data lake using Hudi and Alluxio. In fact, we are currently doing further research and testing. In the future, we hope to have the opportunity to continue share some insights, thoughts, and experience on data lake construction. That's it for today. Thank you.